Hello everyone and welcome to this brand new episode, which is a very special episode again. And in this one I'm going to talk about entity extraction using BERT. So a lot of people have asked me to do this video, and I thought it's now the right time to do this video. And entity extraction using BERT is not very straightforward. You have to think of a lot of different things. And as you can see in the background, there is this book of mine. So if you're interested, do buy it. Don't go for pirated copies. So entity extraction using BERT. So first of all, what is entity extraction? Of course, I'm not going to tell you that. So you have to just see what entity extraction is. I will show you one of the datasets that we will be using today, and based on that we will build a model for entity extraction. So this dataset that I found was annotated corpus for named entity recognition, obviously, and it has two different types of tags: POS, part of speech tag, and IOB tag. And when you use a dataset, you should upvote. So that's what I just did. And let's scroll down a little bit and see this file called ner-dataset.csv. So here what you have is you have the sentence number. So this is the sentence number 1, and sentence number 1 says thousands of demonstrators have marched through London to protest the war in Iraq and demand the withdrawal of British troops from that country. Okay, I didn't realize that it's going to be a long sentence, but yeah. So there is this sentence, and to every word there is some kind of part of speech tag associated to it, and the other kind of tag, the IOB tag. So you have like London is a proper noun, geo tag is associated with it. So same for Iraq, and same for this British BGPE. I don't remember all the things, no, all the full forms here. But I guess it's very easy to just go and Google it and figure out what these tags are. So in entity extraction, what's happening is like you have a sentence and you have different entities associated with different tokens or different words or phrases of the sentence, and you have to extract what kind of entity it is. So entities can be anything ranging from date, time, to year, to name of a person, name of a place, name of some kind of food items, or things like that. And these kind of models are used very widely in the industry these days. So let's say you get an email, and from that email you want to extract all the important dates and times and create a calendar event automatically. So there you can use entity extraction. There are many use cases. This is like one of the use case I told you about. So first of all, we will download this dataset. Now I have already downloaded this dataset, and I have created a bunch of folders called input folder and src source folder. So here I have this ner dataset, so which has sentence number, word, pause tag, right? And I also have BERT base uncased files and BERT base cased. So entity extraction models which you find online, or the traditional entity extraction models, they always dependent on like the casing. So if I write my name is Abhishek, probably the entity extraction model, the traditional entity extraction model, is not going to determine if Abhishek is a name or not, but the new ones might. So let's see the transformer based models. They might be able to do that. So what we are going to do first is we're going to first create a config file. So the config file will consist of a few things. First, we will import transformers. So I'm going to use transformers from huggingface, and then you define a bunch of things like max len. So I will say it's 128. So you have training batch size, Now with 128 I can have a batch size which is a little bit larger for BERT, because BERT takes a lot of space. And then you have validation batch size, and probably 8 is fine. You can define epochs, 10 epochs maybe. So define some kind of base model path, and in my case I have everything in input folder, right? So BERT base uncased. So I think it's an underscore BERT base uncased, right? So we have that, and then we need where do you want to save the model? So model path can just be model.bin. So we just save it in the source folder. And then you have you can have many different things here, but like training file, right, which is input/ner, I think it was underscore dataset.csv, and you have Tokenizer, which is then Tokenizer we grab from the transformers package. So what you can do is you can also use tokenizers from Tokenizer's library, which is also from Hugging Face. But for this video I'm grabbing it from the transformers library. So you have transformers.BERT tokenizer dot from pre-trained, and then here you can write the path. So path will be base model path, and you have one argument, 2 lowercase equal to true. So we lowercase everything. And for BERT base we do need to BERT base uncased, we do need to lowercase everything. So if you use the cased version of BERT base, then you don't need to lowercase. So once you're done with this, you have all the config in one place. So now you can just use config for everything else. And now we will come to the next part, which is dataset. So when you are training a torch model, you need your PyTorch model, you need some kind of data loader, right? So let's import config and let's import torch. And you have to think how this dataset is going to, how this data is going to look like. So I create a new class called entity dataset, right? And inside that I have the init function. So now what do we need? We need texts. So all the text that we have, right? We need the pos tag and we need the tag itself. So this IOB tag, I'm just going to call it tag throughout the video. So I'm going to say we have text, we have pos, and we have tags. Okay, so self dot text is text. Okay, not that. Oh no, sorry. Self dot pos is pos. Self dot tags is tags. So how does text look like here? So text is nothing but a list of lists. Hi, my name is Abhishek. Okay, so maybe there is a comma, and you can see that there is a space before the comma and after the comma. So it's a simple thing. So when you input, you have to make sure that you are tokenizing based on space. Simple. Hello, blah 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 blah, and so on. So this is your texts, and similar to text, you have the tags. Now tags, like, they are probably numbers. So 1, 2, 3, 4, 1, I don't know, 2, something like this, 3, 5, whatever. And same here. So you have this list. Okay, so this is a list of lists, and the next one starts from here, and so on. And similarly, you have the same thing for tags. Okay, so just imagine that we have converted the part of speech names to numbers using label encoder of scikit-learn. So that's what we are going to do in some time. And then you have the len function, which is going to return the length of the dataset, length of self.text. So self.text is list of lists. That's what you have to remember. That's it. Now we define a get item function. Self and item index. Okay, so get item function. So whenever you enter one index 0 to the length of dataset, it will return one item, which will consist of some torts and tensors and stuff. So your training data and your labels. So self.text item. So this is the item that has been extracted. And similarly, you have pause and tags, right? Self.tags, and here it will be self.pause, part of speech, and tags. Now you have all these things. Now the next part comes, which is about tokenizing these sentences. So sentences are currently list of lists here. Okay, so it's not like this, sorry. It's going to be like this. So one token is one word, and so on. Okay, let me finish this one just to make sure everything is correct as examples. Okay, and similarly on this side. So this is already tokenized, but it's not tokenized for BERT. So you have to tokenize it for BERT now. So I will do something like, I will create some empty lists. So this is my list of IDs. Then I need target. So I'll have two targets here, target pause and target underscore tags, or just tag. So I have these three things. And now I will I need to tokenize them. So I can just do for I comma s in enumerate the text. If I enumerate the text, it's going to give me one word at a time, and I can just do inputs is, so I have defined my tokenizer in config.encode, and here you have the sentence, which is just one word in our case. And then you need another parameter, because when you use this tokenizer, it's going to add the special tokens, the CLS token and the SCP token. So you don't need that. So add special tokens is false. Okay, so now the BERT tokenizer has tokenized the input. So if my input is Abhishek, and maybe it's not in the vocab, so maybe it's splitting as like this. Okay, so you are splitting one word to 4 different words. So what is the length of input? Which is quite simple. You can just do inputs, right? And now you take this and extend IDs. So input. So it's just adding to the list. It's like extending the list. It's not appending to the list. And you also do target underscore pos dot extend, and here you do. So now you have the pos tag, which is associated with one word. So pos I, the index, and you multiply it the number of times you have the input len. Okay, so now you have, like, if the name is noun, all of these are going to be nouns. So it's like that. And you do the same thing for tags. Okay, now the next part comes where you want to pad it. So what we are going to do is, I'm going to say my IDs are IDs starting from 0 to config.maxlen, the total length. So we have the length 128 minus 2. So why I'm doing minus 2? Because you need to add some special tokens, and need to do the same for pos and targets tag to just keep them all the same. So once you're done with that, your IDs will become 101, which is the CLS token, plus IDs plus 102, which is the SCP token. So that's how BERT expects this to be. And copy this twice, and here what I'm going to do is I'm just going to add zeros to targets pos and targets tag. Okay, so now all of these have the same length, and mask, the attention mask, will be nothing but ones of the same length as IDs, and your token type IDs will also be the same but with 0. Okay, so now you have everything, except that you still need to pad the input if your input is smaller. So I can just do padding len, which is config.maxlen minus the length of IDs. So that's my padding len. So now I'm just going to pad the inputs, all of these inputs on the right hand side, just as BERT expects it to be. So IDs is IDs plus 0 times empty 0 into padding len. Okay, and let me just copy this thing. So we need mask, we need token type IDs, target pos, target neg, target tag, sorry. So we have the mask and we have token type IDs. All of them need to be the same length, so that's all you need to keep in mind. And target pos and target tag. And now you can return a dictionary. So you can just write return IDs is torch.tensor IDs comma and you need to specify the D type. So torch.long here, because all of them are long ints, right? You need to do the same for mask. Then you have token type IDs, then you have target pause, target neck. So that's all you want to do. And let me just finish this here. Token type IDs will go here, target pause will go here, and target tag. Now for target pause and target tag, it's also the same data type long, because these are also ints, right? And that's our dataset class. So now the next thing that we have to do is go for creating the engine file, which will consist of our training and evaluation function. So we have done it so many times before, right? So it's very easy, but we will do it in a little bit more compact way today. So import torch, and from TQDM, just to monitor the progress, import TQDM, and now you create a training function. What do you need when you're training? You don't need a lot of things, or maybe you need a lot of things when training but not when evaluating. So you have the data loader, you need the model, you need optimizer, you need device, you need scheduler, and that's all you need. Okay, and then you put the model in train mode, and you have some kind of final loss, which is 0. And now we can loop over the batches from data loader. So I can just do for data in TQDM data loader, and here the total will be the length of data loader. Okay, now the interesting part comes is what you can do for k comma v in data.items. So you take everything. So we have always done it individually, right? And you can do data k is equal to v.to device. So now everything has gone to device, and we have already assigned the data type, so it's been taken care of. And you zero grad the optimizer now, and you get some kind of loss from model. So like this. So the only thing that you need to take care of when you build this model, it should take the same input names as you specified in data. So like ID, mask, token type IDs, target pause, target tag. So it should have the same names. That's it. And you can do loss.backward. You can have to do optimizer.step and scheduler.step. So in case you have a scheduler, and your final loss would be final loss plus loss.item. Okay, you have that, and then in the end you return final loss divided by the length of data loader. So that's your training function. Now the evaluation function is not very different, so I'm just going to copy this thing here, call it eval function. So you have the data loader, you have the model, you don't need optimizer, you don't need the scheduler, you need to put the model in eval mode instead of train mode. You need to zero grad, you still have the loss, you don't need backward, optimizer step, scheduler.step, you don't need all these things, and everything else remains the same. So easy peasy. So yeah, less than 30 lines of code for just training in and evaluation, and it didn't take much time either. So yeah, let's hope it works. So we have all these things now, and now we can go on and create our model itself. So model is very important here in this particular problem, model.py. So I will import config because I will need something from config. I will import torch. We will need transformers and import torch.nn as nn because we were returning loss in the engine. So that's what we are going to do. So our model will calculate the loss and return the loss. So we don't need to calculate it inside the engine. And now you have a model. So let's call it entity model, which inherits from nn.module. Okay. And you define the init function. So what should this take? Self for now and nothing else. And this is super titty model init underscore. So now we are ready to write a few things here. So first of all, we will have the BERT model itself. So that's transformers.BERT model. So now we are all aware of the step. So from pre-trained, and here you can have config.base model path. So if you're switching to Roberta, then you just need to change from BERT model to Roberta model, and you also need to change the tokenizer inside config. So that's all you need to do. And now we write a forward function, def forward. So it should have the same names. So let's copy the names. So we have ID, mask, token type IDs, target pos, target tags. Okay. So ID or IDs, I think, mask, token type IDs, target underscore pos, target underscore tag, target underscore tag. Okay, so this is fine. And now we have our BERT model. So this equals self.BERT IDs attention mask is equal to mask, and token type IDs is equal to token type IDs. So I have taken the first input, which is a sequence output, and obviously there is a reason for that, because in this particular problem you are not predicting just one value, you are predicting one value for each and every token, and when that's the case you have to take the sequence outputs. So I can say like BERT output for tag is self dot, now we can also include some kind of dropout here. Self dot BERT drop 1 is nn dot dropout 0.3 maybe, and same for the other one, part of speech. So self dot BERT drop underscore 1, and here you have O1, right? And you can do the same thing for part of speech, POS, and it will remain the same. Instead of BERT drop 1 you're going to use BERT drop 2. And now you have some kind of tag output. So this is like a kind of linear output for each and every word. So what should be the length of this? The length should be determined by the number of tags you have by the number of unique tags you have in the tag variable. So self dot out tag, I can say this is nn dot linear, and I know that I have 768 inputs because it's BERT base, and self dot num tag. Now self dot num tag is not available, so we need to define it. So pause, and I can say that here as input I need num tag and num pause. Okay, self dot num tag will become num tag and num pause. Okay, so we have the tag output now, which is self dot out tag and bo underscore tag, and same thing that you can do u underscore pause, and instead of tag you have pause. So now you got everything, but still there is something missing. So we can return tag, you can return pause, but you also need to return the loss. So you have to calculate the loss. So loss of tag, this loss function. Now this function should calculate the loss for tag and one more for pause. And there are multiple ways of calculating these loss, and you can do loss underscore tag plus loss underscore pause, and you can take an average. You can return an average of these two losses. Now how do you calculate this loss? So let's say we need a few things here. Let's go and define the loss function. Loss function. So we will be calculating cross entropy loss, because you're predicting different tags, right? It's like a classification problem. So it should take an output, it should take a target, right? And here you can define, let's say loss function is n dot cross entropy loss. Okay, now there is a very interesting part comes here, which I have borrowed from Hugging Face's repository. So which says look at active loss. What is active loss? Active loss is where mask, the attention mask value is 1. So you don't need to calculate the loss for the whole sentence, right? You just need to calculate the loss where you don't have any padding. Where you don't have any padding, it means the mask is 1. And then you have active logits. So that will be the same, but for the output. So you can do output dot view -1. But if you do output dot view -1, and if you have like 8 different types of tags, you need to put 8 here, and this number is not known to us now. So I can just do num labels and take num labels as input to this function. So you got this one, and then you need to say, okay, what are active labels? So you have the target already. So what you can do is you can use torch.where, and you can take active loss here, and the second variable will be target. Okay, dot view and -1. So active loss and target dot view -1 have the same length, and here you can do what do you want to replace it with. So torch dot tensor and elephant dot ignore index, and which is of the same type as target. So what's happening here is nothing but we are taking the active loss variable, we are taking target dot view this, and we are saying if active loss is false or 0, then replace it with this value. Now this value you can just do import torch and then define this elephant, and you can print this value. This value is -100. So it's just saying where it's -100, ignore that index for calculating cross entropy loss. and then you calculate the loss, which is LFN. Simple. And you have active logit and active labels. So just ignoring those -100 stuff and return loss. So we can also take a look at it. It's not very difficult. So I can go to IPython, import torch, import torch.nn as n, and then I have, okay, I cannot copy. Okay, I think I cannot copy, so LFN is nn dot gross entropy loss, right? And then you have to print, what is this? LFN dot ignore underscore index. So LFN dot ignore -100. So yeah, that's what is being ignored. So we got everything here. So now we can calculate the loss for both our variables. So what do we need here? We need output, target, mask, and num labels. So output here is tag. Then you have target underscore tag, mask, and self dot num tag. Was it self dot num tag? Yeah. And we need to do the same thing here, but instead of tag, we will use POS, part of speech. Okay. So now this is our model, and I really hope it works. I think everything looks fine now. So we are in the end, we are returning tag and POS and the loss itself. Okay, and everything comes from here. We are returning few more things, so we must fix this, but we don't need them, but we are doing it for, like, if we want to create an inference script. So now we have everything here. So what we can do now is we can create a training script, our final script to train the model. So I'm just going to call it train.py. Okay, so training script. Now here you have to use something that we have already developed some time ago, the BERT sentiment model. So I'm just going to open that one here, and you go to source and train.py. So if you have not seen this video where I built this BERT sentiment model, go and take a look at it. So I will be copy pasting some of the stuff for this video from here, because it's easy, and we have already done that, so why should we do it again? So let's import a few things. So we need pandas for the model, for the data, for reading the data. Import numpy as np. We need numpy, and we will also need torch, and we will need pre-processing from scikit-learn to use the label encoding. We will need model selection from scikit-learn to split the data, and we will need some kind of we will need the usual things that you want to have to train a BERT model, which is an optimizer, the AdamW optimizer that we always use, and linear schedule with warm-up. So other than that, you need config, you need dataset. So these are the files we have created. Engine, you need the model itself from model import. I think we call it entity model. Okay, so you need all these things, and now you can start training models. But you have to first read the data, right? So your data here is a bit different. So you have these sentences and you have the word and you have pause and tag, right? So we need to modify it a little bit. So I will say that we have a function called process data that takes the data path, and this function reads the data in a data frame df pd.readcsv data path. Now I've already seen this dataset, so I know that what kind of encoding to use. So I will use a Latin 1 encoding so that nothing crashes, and then we need to do something. So let's read the data here. And my df will be pd.readcsv ner datasets.csv and encoding equal to okay, I think the name is wrong. Let me see what the name is. ner underscore dataset.csv. Yeah, that's what I'm using. Okay, underscore sorry about that. Okay, so now we have our data frame, but you can see like it says sentence 1 and then it's nan nan nan. Then when you scroll down a bit more, then it says sentence 2, then it's empty empty empty, right? So it's nan values, so we need to fill those values. So to fill these values, it's quite easy with pandas. So what you can do is sentence hash dot fill na, and you can use this ffill method. So now you got sentence 1 sentence blah 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 blah. So now nothing is not filled, right? So you have all the values that you need. So that's what we are going to do here. So sentence number hash, and that equals df sentence hash dot fill na, and here you specify the method ffill. Okay, now you need two encoders. Encoder for pause tag, part of speech tagging. So pre-processing dot label encoder, and you need another one for the tag. Okay, and what we are going to do is we are going to convert these tags. So you can just do df, it should be df.log df pause enc underscore pause dot fit underscore transform. Okay, sorry. And you can do the same for tags. So let's see, what was the name? Pause and tag with a capital T, tag. Okay, now we want to convert this to a list of lists, right? So we need the sentences. Sentences will be df dot group by, you group by the sentence number, and you take the word column and you apply list to it dot values. Okay, so you see what I did here. So I grouped by the sentence number column, and I took the word column, which is like one word, and then so now you have like one word, word 1, word 2, word 3, word 4 in a list, and I converted this to a numpy array. So it's an array of lists. And you need to do the same for pause tag. So I will just copy this thing here, and you also need to do it for tag. So you group by word, and here it will be pause, here it will be tag, right? And then you return sentences, pause, tag, and what else? Encoders, C tag. Okay. So now we have everything. I think we have everything. So I'm just going to read the data, process data, and this will take config.training file. But it won't return the df. So it returns a sentence, pause, tag, like this, right? So let's print sentences, and let's go to our terminal. Okay, we don't want to do that, so I will just do python train.py, and let's see what it returns. BERT Tokenizer. Okay, should be BERT Tokenizer. I hope this works. So it should give me an array of lists of sentences tokenized by whatever token they have chosen. So as you can see, like this is working. So you have this first one, then you have the second list, and so on. And the same is true for the tags, and tags have the same length. So this is one thing that we did. Now I will store it somewhere. I will store some metadata somewhere. So metadata, it's like enc pause. I'm just saving the encoders. So this will be enc underscore pos and enc underscore tag, enc underscore tag. So that's all you need. What is the number of POS tags that you have, which is length of this list enc underscore pos dot underscore classes, and the same for num tag enc underscore tag dot underscore classes. So this is the label encoder object, and underscore classes gives you all the different classes, and you want the length of it. So let's save a few things using joblib. What I'm going to save here is this metadata. So I will just dump without the config. You can dump with the config if you want. So here we are only saving it. So you have the metadata, and I can just call it meta.bin, and it will save me the encoders that I might need for inference step. So we got everything, I think, and now we can try to split the sentences. So train sentences, test sentences, train pause, test pause, train tag, test tag. So we got everything here, and I can just call model selection dot train test split. So there's not a lot of data, so I'm just going to use 10% of data for testing. So here you can have sentences, pos and tag, and I will just say random state is 42 and test size is 0.1. So this will give me everything that I need for training. So now I will copy this from the BERT sentiment model that we built, and copy everything, all the parameters and everything, till we go for data parallel. So in this one, I'm not using data parallel. So we were here. So we have train dataset. Now it comes from dataset, BERT dataset, but we don't have the BERT dataset. We have dataset.entity dataset, I think. Entity dataset. So I'm just going to take this one, and instead of BERT dataset, I have entity dataset at both places. Okay, and what do I have in entity? Text, pos, and tags, right? So I'm just going to take that too and put it here, and remove this one and put it here. So text here will be train sentences, pos will be train pos, tags will be train tag, and here test sentences, test pos, test underscore tag, and everything else remains the same. Instead of BERT based uncased model, we have the entity model now. So let's plug that in. Model goes to device, which is fine. Sorry. Number of training steps, you don't have the length of, there is no df train sentences, everything else remains the same. And let's see what the last part was. So we have the best accuracy, and we calculate the accuracy and stuff and save the model. So let's copy that too. So instead of best accuracy, we now have best loss, and best loss is infinite loss when we are starting. So we have the train loss because our engine returns the training loss now, and we have test loss or validation loss, and we don't need these things. And here I can say instead of accuracy score, I have valid loss, and this becomes test loss and train loss. So we can print both, and this is train loss. So it's easy. When you have done it once, it becomes super easy. Save a lot of time. Instead of greater than, you have now less than, and instead of accuracy, you have test loss. Okay, so if my test loss is, if the validation loss of current epoch is less than the best loss, then it's going to save the model and replace it with best loss, test loss. Okay, so I think we have everything now. We can go ahead and try to train the model and see what happens. So Python train.py. Now I hope everything works here. Yeah, it will take some time. So label encoder object has no attribute underscore classes. Of course, it should not be underscore classes, it should be classes underscore. Okay, one more try. So it's like these type of errors you get, you just open the documentation of label encoder and it has everything. So it becomes very easy. Label encoder object has no attribute classes underscore. Okay, so this can happen when you have not fit the label encoder. I can see enc pos has been fit twice and tag has not been fit. So this is wrong. So you don't get classes underscore if you are not fitting the label encoder. And now I think this should solve this issue, and it should start training the model. We're being very optimistic here. So let's see. Okay, so entity model has two arguments, numTag and numPos, and we created that, but we didn't use them. So numTag is numTag, number of classes in the tag column, and numPos is, let's go pos, number of classes in the part of speech column, different parts of speech. So let's see. One more try. And we need to wait for some time in these cases, because it's doing all the data munging. So what you can do is, instead of reading the full data set, you can only read 1000 rows, and then it becomes easy. So I got some error. So let's see that. Why is this error happening? I think the problem should be in the model somewhere. Syntax complaint. Okay, so this one, it should be outPos. Okay, let's see now. Try to train it again, and I hope it works. We need to wait a few minutes. It's there. So it seems to be working quite well, and now you can train the model on full dataset if you want. So I'm just going to stop it for now for myself, and I've already trained the model previously. So let's try to see how it looks in inference. So I will add the model here later. So I can just do predict.py, which is not much different from training.py, right? So let's copy all these things here, and let's start deleting stuff that we don't need. We don't need all this stuff. We probably don't even need pandas. Maybe we don't even need numpy, but let it be. And we don't need the process data folder. So we need metadata. So we will, instead of grabbing it from here, we will just load it, and joblib, using joblib.load. So let's do that. Metadata is joblib.load, and you have the meta.bin, and everything else comes from there. So enc.pos will be metadata, encoder pos, and encoder tag. So we have that, and we don't need this anymore. We don't need all this stuff. Maybe we need a dataset, and we don't need all these things. We need the model. So we have the entity model, and now we have to load the model weights. So you can just load the state dict of the model. So you can just do model.load state dict torch.load config.model path, because that's where your model is. And you don't need the params anymore. I don't need all of this. So we have the model, and now we need to input a few things inside the model, right? So your train data set. So let's input a sample sentence here that we want to do the tagging on. So my sentence is Abhishek is going to India. So you see, I'm just using lowercase everywhere. So my sentence that I want to supply will be sentence.split. So split by all white spaces. So let's just print the sentence. And now we need to encode the sentence too. So encoded or tokenized sentence is config.tokenizer, and we can just write sentence here, but it should not be here. So we have the sentence here, and so this is only for our reference, this tokenized sentence right now. So we have the sentence, add special tokens, so we can keep the special tokens, doesn't matter. For now it doesn't matter because we are just using it to see how it looks like. And print tokenized sentence, print sentence, or we can just print the tokenized sentence right after the sentence. And we have the dataset, so let's call it test dataset. So instead of trained sentences, we have sentence which is tokenized, which is split, and then you need pause and tags. So you can input anything you want here, right? So what you can do is you can just have zeros times the length of sentence which is split, and you can do same for train tag, because this is test data, so you can have any kind of label that you want, doesn't matter. And now we have to do with torch.nograd, and we can also copy some things from engine.py, right? Or instead of just engine.py, we can maybe let's just copy it. This thing, we don't need anything else. So for k, v in data.items, so your data here will be test dataset 0, because there is only one element, and everything else looks fine. This is, I think, tag, model tag and pause and loss. Okay, tag and pause, we don't need the loss. So now let me copy the model. Okay, so I have copied the model, and here you also need, so this is only one batch, so you need unsqueeze 0th index, because you have to make it batch wise, right? And now you can print the tags. So print tag.argmax, and this will be the second index, the last one, and convert it to cpu.numpy. And okay, let's try this thing. So you can just do python predict.py. BERT tokenizer object is not callable. Okay, so this should be .encode. And okay, so now you see this is our split sentence. This is a tokenized one, and tokenized one, it's adding two special tokens, CLS token 101 and the SCP token 102. And this is our prediction, but this prediction doesn't make sense, obviously. So we will do the inverse transformation on it. So I can just do enctag.inverse transform on this one dot reshape -1, because this is a simple list. So I hope this works, and then we run it again. Let's see what happens now. Okay, so now it is returning me something. It is returning me different tags. So but we don't need all of them, so we only need till length of we only need length of sentence, actually. Length of sentence or length of probably we need length of tokenized sentence. And now let's try to print and see. this thing. So we have the inverse transform, and then we take everything to the length of tokenized sentence, and this is your tag variable. So okay, it is predicting something. Okay, so now we have something. So let's print the other one too, the part of speech thing. So instead of tag, you have POS, part of speech, and that's it. Okay, so now it's done. So let's see. So we know that the first token is the 101 token is the CLS token, 102 is SEP token. So we can ignore this article, but then you see we have person, 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 person. It's because my name is being split into 4 different tokens by BERT, and then you have BERT, which is article is, then we have person 000. So there's something looks incorrect. I think something is incorrect. Let's see if we are doing it right. So we have this tag.argmax2 reshape -1. I guess it's a better idea if I just train the model again. So let me do that quickly. So instead of training, I went for a lot of investigation, and I found out I made a major blunder. So here is the blunder. So this should be outside the for loop, and I really hope that this fixes our stuff. So let's see. It's the same model, so I did not train the model at all. Okay, so it looks a little bit better now, but I won't say it's properly fixed. So maybe I need to train the model again. So after training the model again, let's see the results one more time. Things are not going my way, it seems. Yeah, okay. So now it seems to be much better. So we had a major blunder. So we have 101, which is CLS, and then 102 SEP token. So this and this we can ignore, and rest. My name is split into 4, so that's person token tokens, and then other. Then you have geo token, which is India, and same here. So you can see that 2 goes to 2, and you can ignore the first one and the last one. So finally we were able to build a model using BERT for entity extraction, and this is like one of the state-of-the-art models right now. So you can take this code the way I've done it. You can extend it to a single type of entity for almost any kind of dataset you want, and you can very easily change from BERT to Roberta or to any other transformer based model that you want. You just need to take care of the tokenizer. One thing I've not shown you here is how to assign this word to this entity, but that's something I will leave as an exercise for you, and if not, I will try to do it in one of the next videos. And thank you very much for watching today's video, and I'm sorry about all the mess that happened, but everything works, and you will find the code in the GitHub repository as it is. So take a look and train your own model and let me know how was it. Thank you very much, and like if you like the video, and do subscribe. So thank you and see you next time. Bye.